Hello guys, welcome back to my YouTube channel. Myself Girish BB. Currently I'm studying in Sri Venkateswara College of Engineering, Bangalore from the Department of Information Science and Engineering. In this video, we are going to discuss about the most important topic, that is lists. In the list, doubly linked list, additional link, list operation, sparse matrix. Lists. First, the topic doubly linked list. Here's a simple representation of a doubly linked list node is a programming context. Previous data next traversal in a doubly linked list can be done in both directions, forward using the next pointers and backward using the previous pointers. This makes operations such as insertion and deletion and more file efficient in some cases compared to singly linked list. Next, doubly linked list is a data structure in computer science that consists of a sequence of elements where each element points to both its procedures and successors in the sequence. In contrast to singly linked list, where each element only points to its next element, a doubly linked list allows for traversal in both directions. Each element in a doubly linked list, commonly referred to as a node, contains two pointers or references that are data or value, next pointer, previous pointer. First we should discuss data. This is the actual data or value associated with the node. Next pointer points the next node in the sequence. Previous pointer act as a points to the previous node in the sequence. Next, logical representation of a doubly linked list. First null, previous data, next head. Previous data is a head, previous is null. Here previous data next and previous data next equals null. Next, advantages. Bidirectional traversal. Easy traversal in both forward and backward directions. Ease of deletion. Deleting a node requires only adjusting the pointers of its neighboring nodes. Insertion and deletion at both ends. Operations like insertion and deletion at the beginning and end of the list are efficient compared to a singly linked list. Next, we should discuss about the disadvantages also. First one, extra space. Second one, complexity. First, extra space requires additional space for the previous pointers, which can increase memory overhead. Next, complexity. Increased complexity in terms of implementation and maintenance compared to singly linked lists. Next, here's a simple example of a doubly linked list node in a hypothetical programming language. Class node definition int self data equals data, self dot next equals none, self dot previous equals none. Then in real world applications, doubly linked lists are used in canaries and bidirectional traversal or efficient insertion and deletion at both M required. Next, doubly linked list node declaration. How to declare the doubly linked list in this slide. Here class node definition int self data equals data, self next equals none, self previous equals none. Like data, it's represents the actual data or value stored in the node. Next represents points the next node in the sequence. Again previous points to the previous node in the sequence. Next, doubly linked list operations. A typical operations performed on a doubly linked list that are insert, delete, search, print. First we should discuss about the insert. The insert operation in a doubly linked list is performed in the same manner as a singly linked list. The only exception is that the additional node pointer previous is also required to be updated for the new node at the time of insertion. Next, we should discuss delete. The delete operation in a doubly linked list is performed in the same manner as a singly linked list. The only exception is that the additional node pointer previous of the adjacent node is also required to be updated at the time of deletion. The next, search. The search operations in a doubly linked list is performed in the same manner as a singly linked list. The doubly linked list also provides the additional flexibility of starting the search from the end and moving backwards towards the front. The next, print. In the print operations in a doubly linked list is performed in the same manner as a singly linked list. The doubly linked list also allows you to print the list element in reverse order by starting from the end and the backwards and the front. Next topic is sparse matrices. Sparse matrices are matrices that contains mostly zero values. They are often encountered in various applications, such as in representing graphs, images, and scientific simulations where a large portion of the matrix elements is zero. There are different ways to represent sparse matrices, and one commonly used representation is the compressed sparse row, that is called CSR format, means compressed sparse row. In this format, you store only the non-zero elements along with their row and column indices. Here's an example C program that demonstrates the creations and printing of a sparse matrices in CSR format, means the compressed sparse row matrix format. Next, in the previous slide, one example is there. That examples in that example, the elements represent the structure and a non-zero element with its value, row index and column index. The sparse matrices. This structure is represents a sparse matrix in CSV format containing information about its dimension and an array of non-zero elements. Create sparse matrix. This function creates a sparse matrix. Print sparse matrix. This function prints the sparse matrix in CSV format. Node structure of sparse matrices. When representing sparse matrices, you can use a linked list structure to efficiently store only the non-zero elements along with their row and column indices. Each node in the linked list represents a non-zero element. Here's an example how you might define the node structure for a sparse matrices in C. In that structure, the row represents the index of the matrix and the column represents the column index of the matrix, and the value is actual value stored at the specified row and column. Then in the next row, pointer to the next and non-zero element in the same row. Next call is represent the pointer to the next non-zero element in the same column. Then the last topic is linked representation of sparse matrix. A linked representation of a sparse matrix is a way of storing sparse matrices efficiently by only storing the non-zero elements along with their row and column indices. This representation helps save memory compared to dense matrix representations where all elements are stored. There are different linked representations for sparse matrices, and one common approach is using a list of lists or a linked list of nodes. Here's an example of the representation of sparse matrix using linked list. You can see here. In this representation, each non-zero element is stored in a node. and the nodes are connected based on their row and column indices. This allows for a more flexible structure to represent sparse matrices. These are simplified examples, and actual implementations might involve additional details, but they capture the essences of linked representation for sparse matrices. Then advantages of sparse matrices. Memory efficiency. Sparse matrices store only non-zero elements, saving a significant amount of memory compared to dense matrices. This is particularly advantageous when dealing with large matrices where a majority of elements are zero. Next, computational efficiency. Sparse matrices can lead to computational efficiency in certain operations. For example, in matrices multiplication, the number of multiplications can be reduced since many elements are zero. Algorithms can be designed to take advantage of these sparse matrices, leading to faster computations. Reduced storage requirements. Sparse matrices represents reduced storage requirements, which dealing with large datasets or when memory resources are limited. Then disadvantages: complexity of implementation, overhead of data structure, limited applicability. Implementing operations on sparse matrices can be more complex than dense matrices. Specialized algorithms are often needed to take advantage of the sparse matrix efficiently. Overhead of data structures. The use of linked lists or other data structures to represent sparse matrices introduce some overhead which may be impact performance for all matrices or simple operations. Sparse matrix representation are most beneficially when large properties are zero. In situation where matrices are dense, the benefits of a sparse may be language. The last topic, additional list operations. In addition to the common list operation like indexing, slicing, appending, and removing elements, there are several other useful operations and methods you can perform on list in programming language like Python. Here are some additional list operations that are concatenation, repetition, list compression, sorting, reverse, membership, test, count, clear, extend. First, concatenation. It means combining the two or more lists into a single list. One example is here. One example is there here. That is list 1 equals 1, 2, 3. List 2, 4, 5, 6. Concatenated list means combining the two lists, and that means list 1 plus list 2. Then print the concatenated list. The output is 1, 2, 3, 4, 5, 6. Then the repetitions. Original list equals 1, 2, 3. Repeated. The repetitions means creating a new list by the repeating the elements of an existing list. Original list equals 1, 2, 3. Repeated list equals original list star 3. Original list you already know 1, 2, 3. Star 3 means multiplied. Then print the repeated list means it repeat 1, 2, 3, 1, 2, 3, 1, 2, 3 in 3 times. The next, list compression. A concise way to create a list using a single link of code. Squares equals x star star 2 for x in range 5. Print squares. The output is 0, 12, 15, 16. The next, sorting. Sorting is a sorting the elements in the list. Numbers 3, 1, 4, 5, 9, 2. Sorted numbers equals sorted numbers. Print the sorted numbers means 1, 1, 2, 3, 4, 5, 9. The next, reverse. Reverse, it acts as a reversing the order of element in a list. Then numbers equals 1, 2, 3, 4, 5. Reversed numbers equals list reversed numbers. Print reversed numbers. It prints the reverse order 5, 4, 3, 2, 1 like this. Next, membership test. It means it's act as a checking the element, if an element is present in the linked list. Example, fruits equals apple, banana, orange. Print banana in fruits. The output is true because banana is there in the fruits list. The next count. Count is acts as a counting the occurrence of a specific elements in a list. Example numbers 1 2 2 3 2 4 2. Count the twos equals numbers and count 2. Print of count twos. The number of 2 in the numbers equals 4. Then clear its acts means is it's removing the all elements from a list like numbers equals 1 2 3 4 5 numbers dot clear and print numbers. The output is only square brackets, all numbers are cleared. The next extend means adding elements from another list to existing list. Example list 1 equals 1 2 3 and list 2 equals 4 5 6. List 1 dot extend list 2 print list 1 1 2 3 4 5 6. It adds list and 1 and list 2 both. Next, inserting a single linked list. Inserting element in a linked list can be done at the beginning, at the end, or at the specific position within the list. Here are example of inserting element in various ways. You can see the insert the beginning and insert the end and insert the specific position for each example is there in this slide. The next advantages: expressiveness and conciseness. Additional list operations such as list compressions allows for concise and express code. This can lead to better readability and more straightforward representation of certain operations. Efficiency in specific scenarios. Some additional operations like list compressions and sorting are optimized in many programming languages and libraries. Leveraging these operations can lead more efficient node, especially when compared to writing equivalent logic manually. Memory efficiency. Certain operations such as list compressions and slicing can be efficiently in terms of memory usage. This can be crucial when the data sets are in more memory constrained environments. Disadvantages: complexity and readability, overhead in performance, memory usage. Some advanced list operations, especially those involving list compressions with complex expressions, can reduce code readability and make it harder for others. Certain operations such as sorting or reversing a list may have performance overhead compared to custom optimized algorithms tailored to specific use case. In performance critical applications, it's important to consider the efficiency of operations. Certain list operations like copying or extending a list may lead to increased usage, especially when working with large data sets. This can be concluded the constrained environments. Thank you for watching my video.